have people joining from all over. So thank you so much for such a strong turnout. On behalf of the IEEE PES Task Force on Foundational Model, would like to welcome you all in this new series, the webinar series that we have started. Today, we are very pleased to host Dr. Hendrik Hamann, who is a professor at Stony Brook University and the AI chief scientist at Brookhaven National Lab. Prior to that, he spent over 25 years at IBM Research, where he served as chief science officer and led the development of a geospatial foundational model. Dr. Hamann has authored over 260 scientific papers, holds 180 patents, and is a fellow of the American Physical Society. Today, he'll be presenting his talk on GridFM, a foundational model for the electric grid. Following the presentation, we'll have some time for Q&A. So feel free to post your questions in the chat as they come up, and we'll gather them for discussion towards the end. And with that, let's get started. Hendrik, thank you for joining us, and over to you.
Okay, so let me share my screen. Okay, so again, apologies for this. So I just had to grab some charts which I have, but I hope you get a good feeling for what we have been developing for foundation models for the electric grid, right? Of course, some people ask me, why do we need a foundation model for the electric grid? Or why do we need AI in the first place for the electric grid? And the way I like to think about this is, of course, we have a growing electric grid. We have the emergence of AI data centers. There are certain capabilities which we have today through traditional, typically physics-based simulation techniques, which is sort of depicted here in this green circle. But as we are increasing the system size, as we are increasing the uncertainty, as we need to run more scenarios, as we want to do more comprehensive planning, there is this need for acceleration. There's a need to create computational technologies, right, through AI, potentially, which allow us to deal with this increasing complexity and uncertainty of the electric grid as it is evolving, as it is driven by so many trends, as we all know. So that's a high-level pitch for why AI for the electric grid. Now, of course, people ask what kind of AI, right? And AI has been around for quite a long time. And in my mind, it's always kind of useful to look into the history of AI, right? It kind of started even before the 80s with expert systems, but machine learning were really rather simplistic techniques, but basically specific inputs and specific models. Then deep learning came along around 2010, right, when we had actually an IBM Jeopardy, which allowed us to discover the input features automatically. But the models were still task-specific, and now more recently we have these ideas of foundation models, right? Foundation models are models which, as you know, are trained on very large data sets. There's this idea of self-supervision. You train them for a broad set of tasks and problems and applications. They are, for example, of course, we have seen the big successes in text with these foundation models. And of course, they're all enabled by massive access to data and compute. And of course, they have been pioneered in form of large language models. Now, just for everyone, so they understand what the process of a foundation model is. Really, foundation model has 3 steps. I explain it here with the text modality, but there's three different steps. There is an initial step, which is the pre-training of a foundation model, and you use self-supervision, which is a brilliant idea, which is the idea that I take a data set and then I mask part of this data set, and then you use attention network to ask the model to learn what you have masked. So let's say you have a sentence: in the morning I drink a cup of coffee and eat a bagel with cream cheese. You would mask part of that sentence, and you ask that model with an attention network to learn how to fill in these missing tokens. So you would teach the model that the word coffee is close to the word morning, that the word bagel is close to the word whatever, cream cheese, etc. So you would teach the model the fundamentals of how language works. You would teach the model to do an excellent job in next or missing token prediction. That's basically what these models are really good at. And so then once these models have learned, the basics of language, let's say, right, for LLMs, it's similar to how we learn as people, right? So you basically learn this, and then you go to college and become an expert in, let's say, power systems. So you get fine-tuned. So you feed that foundation model, so you update the part of your model to become really good for, let's say, power systems. And then, of course, the final step is the inference, where you basically operationalize this. Now, in the foundation model world, the pre-training, again, tries to be somewhat agnostic to the actual, tries to be quite general, so you can address multiple downstream tasks. It is an expensive step. You typically use, you have a very large model typically. You have a billion parameter model. In language, you have trillion parameter models, etc. So it's a very expensive undertaking, but once this is being built, the fine-tuning is relatively fast, cheap, and easy. And then, of course, the operationalization and inference is even less costly. So that's typically can be done even on CPUs or single GPU type of workloads. But the idea, of course, is you build a foundation and you get that investment you made into that foundation back by fine-tuning this. Now, you guys know, of course, that from experience, let's say ChatGPT or any of these other large language models, that they are massively successful, that they have actually lived up to some of their promises for sure. But then, of course, that really raised the question, and there was a question which we had quite a while ago already, is whether we can invent a foundation model which is not pre-trained on general language, but which might be tailored to the electric grid, which is pre-trained by different electric grid data, etc. And so that was really a question which we had, which was 2 years ago. That's really where we started. Now, we had some prior experiences with training sort of non-text-based foundation models. So it was actually mentioned in the introduction. At that time, I was still in IBM. We worked quite a bit with geospatial foundation models, so with foundation models for weather or for remote sensing. And of course, we had a lot of experience gained through that. And I just want to show how we trained foundation models for weather or for Earth observations. And the way you do this is, right, you have, let's say, different weather fields or geospatial imagery observations. You have this at different timestamps. Typically, a foundation model is a transformer-like architecture. So there's an encoder, there's a decoder, and then what you would do is, right, similar to what I've shown you in the text domain, is where you mask missing words. Here you mask different parts of that image, so to speak, or of that array, and then you train the model to predict the missing parts. And that created something like a weather foundation model or a foundation model for Earth observation. Now, if you really look under the hood, of course, there are multiple ways you can train these foundation models. You can mask spatially. You can mask, of course, also temporally. But you can also mask between, in this case, different layers. Let's say you would have precipitation and temperature, so you would force a model to learn from temperature to precipitation and vice versa. So there are different pre-training strategies that is actually very important if you want to understand what your model can do and what it cannot do. And so it's something which will come back later when we talk about the grid foundation model. What had we learned from this experience with non-text-based foundation models, let's say for weather? We learned two key things. The one thing we did learn is that for forecasting, but also for filling in missing values, these models, which we trained, let's say, on weather data, so basically were emulators, right, for emulating what traditional weather models would be doing, they're actually performing very well. So we learned that, yes, we can build AI models and foundation models for something as complex as weather, which actually perform quite well on forecasting tasks. The second thing we learned is, and the second might be not really surprising, is, but of course we learned also that an AI emulator fundamentally is much faster than these traditional weather simulation weather models, but in some cases by 5 to 6 orders of magnitude. So in fact, in the chart here, we compared our foundation model, which is the first one, which was 40,000 times faster on a single 4-GPU A100 node compared to the actual performance which you would get if you would deploy it to one of the fastest supercomputers. So enormous acceleration through the emulation at competitive or even better accuracy. So that's what we learned. So in order to understand really, right, how these experiences which we had now from weather could be applied to the electric grid, we started in 2024 to build a community which we actually call the GridFM community. So it's a community of scientists, folks from industry, folks from academia, national labs, other stakeholders, where we basically just try to figure out as a community jointly how can we build a foundation model for the electric grid, because that can mean many things to many different people. This is not quite updated, but it shows you sort of the history of this community. So we started way back in 2024 with a workshop. We created a perspective paper. We have now over, this is outdated here, over 400 members, maybe 120 organizations. We meet once a month. So if people are interested in helping us on or in joining that community, they can go to gridfm.org. You can sign up there, and we have monthly calls, etc., where we're basically exchanging across that community of people our experiences with building these foundation models for the electric grid. Now, this community we ask really three questions in our when we started conceptualizing a foundation model for the electric grid, right? So the first question we ask basically is, if you think about the strengths of foundation models, right? What are they really good at, and how would they map to what is important in power systems? And so we created this table, which I think is a really good table. If you think about it, right, AI foundation models are really good in this next data token prediction problem. And that's, of course, enabled by transformer architectures and the attention networks. And of course, if you think about it, how many next data prediction problems do I have in power systems? It turns out you have actually a bunch. Power flow, any type of forecasting, etc., etc. So just simply the fact that these types of networks and this type of training is actually good for this next token prediction problem shows interesting opportunities for the electric grid. The second thing these foundation models are really good at is, of course, just the way they're built, they're large and they're trained on rather diverse data sets means they can be adapted. And of course, that's also really useful for power systems because in power systems, we have, of course, different grids. We have, in the United States, we have 2,000 different, maybe more than 2,000 different grids. We have all these different applications, requirements, markets, different weathers. So the fact that we can build something which we can harmonize across different applications, I think is also really important. And then the other thing, and I showed that, is that we have this massive acceleration over simulations. And I think there is a lot of opportunities in the electric power systems as our power systems get more complex and more uncertain for acceleration in expansion planning, in the interconnection problem, contingency analysis, co-simulations, etc., etc. So there is a bunch of these kind of things. The second thing, of course, we ask is, now let's say this is all true. How can you build a foundation model so you can actually, it can address many, many applications because it's a big investment. And so you want to build something you can actually fine tune to a large set of applications, right? So what knowledge do you have to encode in your foundation model so it is really useful for multiple applications? And then the third thing is we looked into sort of practical things. Can we actually build it, right? Yes, there are advantages. Can we define exactly what knowledge we encode, and then can we actually build this? Now, an initial answer we came up with is this idea of a foundation model. It's a really basic example, and we call it GridFM version 0. But let's build one on power flow. And the reason for power flow was because of its broad utility, of course, in power systems, because it lends itself really well to what the foundation model is really good at. And so we started with building a foundation model which is pre-trained on power flow data. So how does it look? Well, you have conceptually here your grid. And so you have your load buses, generator buses, slack buses, lines, etc., etc. You have your different values, active, passive power, voltages, the phase angles, etc. You mask in the same way you mask the words in the text, in the same way we mask the different patches in weather and the forecasts. And then we train a model which learns how to reconstruct that graph, these values at the graph. So that is a very basic thing which we started working with. So people ask us, of course, where did you get the data from? Well, we basically started with synthetic grids and created synthetic data. I'll show this in a second, but of course you guys know there are all these synthetic grids which are available, and we take them and then we solve for power flow, and that is our training data. There is a full tool which we developed, which you can get on the Linux Foundation for Energy, the GridFM project, which is called the data kit, the GridFM data kit. And this is exactly what it does is, so you can load your case file, your topology in. It has a way of applying different load profiles, load scenarios, their bus level and load perturbations it applies, which you can specify. It also applies topology perturbations, and then it solves for optimal power flow, as well as for contingencies, the power flow values to create you a very large, diverse data set of different simulated grid data, which you then can use to train your model. Okay. So once we have that, we build the foundation model from this data set, which you have here on the left side. Of course, you got to normalize your data. You got to do the masking. We have a 0.5 probability masking, so we mask randomly. So we are not masking based on power flow because that would be the fine-tuning task. We just want the system to understand the relations between the different variables. Again, there are many, many different grids we feed into this. And then we do the GridFM pre-training, which is basically a graph neural network. And then we have a physics-informed loss function, which also takes into account the power balance. So it's basically a linear combination of a mean square error and a power loss, power balance energy loss. So this shows you super simplistic, right, what this is on a toy example, but you have your numeric solver, you mask, and you do the GridFM reconstruction. Of course, you can compare your reconstructed values to the actual numerical value. That gives you then the actual error metrics which you train on. And of course, you also reinforce the power balance on this. The next thing we did is we said, okay, this is all great. So let's do a little toy experiment and start with a foundation model, which is trained on, so this was very early work, which we did earlier this year, at the end of last year, but we took 5 different networks. And then we went to a much larger network, the Case 300, which of course you guys all know. So pre-trained was on these 5 small networks. And then what we said is, okay, does this foundation model has learned anything useful? So there is a benefit to fine-tuning it on a Case 300. So we took it now to a new grid, basically. And of course, you do that test. And what you see is that the pre-training, although this was done with much smaller networks, drastically helps with the convergence speed of the model, which is now pre-trained on the 300. And of course, the other nice benefit you can get is you can get much better data efficiency, which means you can actually train your model with significant less data. So that's great. We also looked into the speed. This is a little bit outdated, these data points, so I want to apologize for that. But of course, you also see that this foundation model, which we have, not quite as accurate as an AC power flow solver, but significantly more accurate than a DC power flow solver. These are the blue points we have here on the y-axis, the actual error, and here's the compute time. Our foundation model is, of course, much faster. It's more accurate than the DC power flow solver, and it's not quite as accurate, although we're working on it, than the AC power flow solver. So that's sort of what we got. We have done much more progress in the meantime. Now, one of the applications we are using it for is actually contingency violations. And if you look into the contingency violations, let's say you do an n-2 or n-3, and you compare our GridFM model in terms of contingency violations as a classification task, you can see that we're outperforming the DC power flow solver, of course, significantly in terms of speed, but also in terms of, in most cases, in terms of accuracy. But then we get very high accuracy on the order of 99%, etc. Another interesting use case we are looking into is creating what I call data center hosting maps. Think about it. We have now an accelerated power flow solver. So can we actually create data center hosting maps by looping through, by basically identifying connection points in our electric grid using the accelerated the acceleration which we have with this grid foundation model to help with the interconnection problem. So just to remind you, right, if you connect a very large data center to the electric grid, if that's what you want to do, is, you know, it's a long process. You at some point get to a system impact study, and at the system impact study, roughly after 1 or 1.5 years, you will learn whether your whole process takes 3 or 5 years, and you will learn how much potential additional cost you're going to have and how much delay you will have. So the idea is, can you create sort of a pre-screening step here? This is sort of where this is sort of illustrated. This is just a toy example which we ran, but of course some people know there is this synthetic grid in Texas, 2,000 nodes, developed by Adam Birschfeld, which is really useful under an API program. And in this particular case, we were just looking at 1,000 different load connection points, and you can just do that math in your head. But basically, you can say, if I want to figure out, okay, what is the likelihood of what is the likelihood of a fast interconnection process? You can connect hypothetically, let's say 100 megawatt load to 1,000 different connection points. So you basically loop through this. Then once it's connected to each of those connection points, you run it for 4,000 contingencies, which is roughly the numbers of contingencies which you have in this grid. You do this for, let's say, 10 different loads, meaning 24 hours, and then that is 288 different loads, and you run the math, you're going to be ending up with billions of power flow simulations. So we did some benchmarks. If you wanted to do this with a conventional solver, this might take you on the order of 450 CPU days. Of course, you can have 450 CPUs and compute it in a day, but by way of comparison, an AI emulator would be able to do this in just 2 days. So this is something we're working on. We already have some results, so it's kind of quite exciting. Let me just say a few words before I will open it up for questions. How do we actually advance GridFM, and what is our bigger vision? So what we have today is, and I brought this up early on, right, when I talked about the different ways to pre-train. What we do today, this is really what we do today, is we're basically masking values on a graph, and then we train a neural network to reconstruct these values. And of course, that enables different applications, a version of optimal power flow, state estimations, contingency analysis, load flow, etc. And that's all cool. But of course, the next logical step will be to, because remember, we have load profiles. If the load profiles are sensible, then we can also learn the temporal dynamics. So which means we would not only reconstruct for the different values or different features at the different buses, but we could also reconstruct for the next value, so do temporal reconstruction. Of course, that would bring us into forecasting, load forecasting, look ahead power flow, look ahead state estimations, and of course, we would need to have different training data, but we could extend this to transient stability analysis, and some of the people in the larger working group are already doing this. Now the third piece of this puzzle is this edge reconstruction. So maybe we can also learn to train the model to reconstruct the missing edges. And so, of course, that brings up a whole bunch of other really cool opportunities like expansion planning, cybersecurity applications, control, operations, etc. So in the big picture, this is really how we envision advancing the foundation model. Within that larger community of GridFM, we have folks already looking into the temporal reconstruction task. We have different efforts, but I think the fundamentals, right, of building sort of a foundation which where you do different pre-training tasks, you bring different networks in, you build a very diverse data set, and then you can apply this and fine-tune it to different applications is actually quite promising. There is a sort of a roadmap which I like to show. So our next version will really looking into bigger models. Currently, we have a relatively small model. The one you pick up at the Linux Foundation will be on the order of 1 million, but this is a little bit outdated. We already have started building larger models. We have additional data representations. We're looking into different architectures, especially how to bring in the global context in a more efficient way. We have load profiles now, which are much more realistic, which we got from deaggregation. We're looking into different pre-training strategies, as I was pointing it out. And just to summarize this, you can go here to Linux Foundation for Energy. There you find the GridFM project. These are the two toolkits, the data kit and the graph kit. As I said, the data kit is a universal, but it's a pretty nice tool to create large, diverse training data sets. And then the graph kit is basically the foundation model, which you can use for training, fine-tuning, and interacting. There are examples of that, and that's sort of where you can actually consume this technology. I think with that, and I was rushing a little bit, but I think I wanted to leave some time for questions. And of course, I was 15 minutes late, but I hope you get a really good feeling for where we are and the progress which we've made. And thanks so much. And I hope there are many questions. Thank you.
Thank you, Hendrik. I think that was a great presentation. And audience, like, feel free to post your questions. I already see some questions in the chat. But before that, there's one question that's coming up, and it's more so about the generalizability of this model. So I think you mentioned in the in some of the earlier slides that it has been pre-trained on some networks. So how do you see this GridFM applying to, let's say, large scale grid, or let's say grids whose configuration might be, let's say, different from the training data?
Yeah, so let me say, and I was a little bit grabbing the charts which I had, right? So we've extended it now to grids which are on the order of 5,000 nodes, right? So that's a smaller transmission grid. That might be New England ISO, etc., etc. So in this particular case, we are going from case 118 to case 300. And we see benefits. That does not mean it's robust, but we see the benefits of the foundation model pre-trained on these smaller grids as we're doubling the node size. And the benefits are, and you can see this on this chart, is that we can get away with significantly less training data in the fine-tuning step, which is a step here, right? So we can get away with way less data for this case 300. And the other thing is it also converges significantly faster, which is another benefit. So we know that. Now, what is really important, once this model is fine-tuned, let's say we have it now fine-tuned for case 300. We ran, and unfortunately these, I don't have the charts in this deck, we ran systematic studies now. How robust is that model against small topology changes within case 300, right? So because we want to run contingency analysis, or we want to run n-10 contingency analysis, so there might be 10 changes, etc. So we have done systematic testing on a 2000 grid, the Texas 2000 grid. We find that that is for N2000. So we went from 300 to 2000. So it's a different foundation model, but and we found that that fine-tuned model for the Texas grid is topology robust all the way up to an N-10 to N-12. And after that, we start losing accuracy. And so we're still investigating that, but that's where we are at this point.
Okay. I think we have a lot of interesting questions coming in the chat. So I think I'll pick one of those. It says, I was wondering if we have applied this foundational model in an industrial setup, or do you think it's still like a proof of concept and we still need to do some work before it could be applied to practice?
I think there's still a lot of research work we can do, we should do. In parallel, I think it's also good to test it at least, right, in industrial settings. So we are not really focusing on the wrong things. So for example, right, a really good use case, and I brought up this use case, is this expansion planning, right? Expansion planning, in my mind, is a really good use case for this technology because as you look into different expansion options, you have literally billions of different options, right? How you could extend that grid. And of course, the speed of an emulator could really help you out there. And I think that would be a really good industrial setting because it's not something operational, it's something you can study, it's something where you can actually find out later how good it is. So you're not breaking anything immediately, and it would really be quite a useful tool. And we also know that even this GridFM is doing actually better job than DC power flow, which is typically what they use for expansion planning.
There's another question that says that's on the pre-training dataset that was used for this foundational model. So how big was that, and how much? What's the scale of the dataset that you used to pre-train these models?
Yeah, so the whole data set for the so let me just explain so everyone is clear about this, right? So of course, this tool which we're showing here, which is this data kit, right? You found it on you will find it on Linux Foundation. What we've done for the foundation model, we have taken many different grids, around 10, and then ran that through this whole process. That data set is on the order of, it's not super big, it's a terabyte or something, on the order of a terabyte. Now, let's say you wanted to fine tune for one particular grid using, you can use, right, for the fine tuning, you can use that same data kit to generate yourself the training data. Yeah, so you would have maybe 50 megabytes or something for Texas 2000 grid. That's what you would end up, right? So the pre-training we did is a terabyte. I want to do now fine-tuning for Texas 2000. That's a synthetic grid. I would have maybe 50 megabytes or something like that.
I see. Thank you. I think there's another question. So there was a big audience from ISO. So there's a big ISO community that joined us in our call today, and somebody is asking, how can someone at, let's say, KAISO can pick up one of these models and test how path flow results or contingency analysis results can be predicted? So so where exactly should they go to find these to find some of these models and try to test on some of the networks that they might have?
Yeah. So thanks for the question. Right. So we are. Let me just say. Right. We are. So GridFM is a community. I think the number one thing would be to engage with that community. You can start with me, but you can go to the webpage. You can sign up. We have different working groups. What we're trying to do is we're trying to sort of join forces. So let's say there's another ISO who's also interested in that. So we don't need to do a test case maybe with the New England ISO and California ISO, et cetera, et cetera. So we channel that. We have certain sub-working groups. But having said that, we're super happy to work with anyone, right, who wants to use it. You can also pick it up here on Linux Foundation. There are examples. This is not yet here, but we're also going to have a collab, which is the easiest way you can get started with all this stuff, right, which is basically just a notebook on Google Cloud. Yeah, but please reach out to me. We're super interested in working with you. I do believe it really depends on the different use case you want to try. Contingency is a great use case. Expansion, I do believe, is also very good. We have sub-working groups working also on state estimations and other use cases. But yeah, please reach out to me.
Yeah. I think we have another interesting question. So it says, so the model that you have released, has it been trained exclusively on the simulated data, or you have used some historical data to train any of these models?
So far, it has all been trained on simulated data, right? Yes.
All right then. There is another question that asks, does the foundational model handle discrete devices such as automatic tap changing transformers, capacitor banks, and reactor switches?
Yeah, it does. It does, right? It's a question of, how you generate that. The data toolkit, again, this is something we're building, right? So again, you can find it here, you can contribute to it, etc. It has certain capabilities that's all described in terms of, for example, different switching positions, etc. There might be work we can do to enhance it. But in general, the model handles it, of course. Yes.
There is another question on state estimation. So one of the participant is asking, can you speak to the use case of GridFM for state estimation instead of replacing power flow using GridFM to estimate model parameters that better reflect measured operational values?
Yeah, so there is a subgroup working on the use case of state estimations, right? And I think it's it's a good opportunity for GridFM, right? We find that so again, this is early work. I don't have the charts in this deck. We can follow up on it, but we find, for example, that compared to traditional state estimations, using a grid foundation model, you can actually get uh, the same level of state estimations with less measured values, and of course that is great. You're more robust against outliers. Yeah, so it's definitely an interesting use case, right? We're looking at it would be it's right in the wheelhouse of what this model can do today.
Okay, okay. There's another good question. So somebody is asking, how does the data generation process work for contingency scenarios that cannot be solved with direct AC/DC path flow? Example, dynamic stability analysis. If these scenarios are these scenarios not included in the fine-tuning process, or is there any expectation that the fine-tuned model could handle these cases?
Yeah, very good question. They're not included currently. So something which doesn't converge is not included in the fine-tuning. So it's a good question, something we need to investigate a little bit better. But really good question. No, we're not excluding it, right? Then remember the one thing, even with GridFM, the one thing we do is, of course, not only do we have in the loss function the power balance, right? But once we have the result from the power flow analysis, we can obviously check the validity of that power flow analysis on the AI side, right? So it's really important. So we're not trusting just blindly our AI model, but we can always check whether that AI model, by plugging it back into the power flow equations without solving them actually, but we can plug it back in to verify that we have solved it correctly.
I think there are a lot of questions around, in general, the model architecture. How can people learn more about how exactly this model was built, like what sort of data was used? So a lot of them centered around model architecture.
Yeah. So let me just say, we're just preparing a paper, a white paper will be on archive. You will find it also here on GridFM. There will be you're also going to find it on Hugging Face. So there will be a more technical description on all the parameters, what it was trained. You already have some of that if you go to the pages, which tells you a little bit what was it actually trained on, all these details. You find that if you go actually to Linux Foundation for Energy, you click on the GitHub thing here, right over there, where my cursor right now is, and then you get to the GitHub, and then you can actually find out some more information. But there will be also a proper write-up about it.
Perfect, perfect. I think we have a lot of questions, so I think maybe Hendrik, I'll compile some of these questions and send them your way. And looks like we are at the very last minute, but thank you everyone. I think we had participants from over 15 countries today. There were over 250 people who joined us today. So thank you everyone for joining this webinar. The recordings would be made public in YouTube. And Hendrik, if you want to share some slides or any of the materials that you think would be useful for the participants, would be happy to share with them. And yeah, and thank you for the presentation. It was really well.
Thank you.
Thank you.